Hey guys, Buildzoid here, and today we're going to be taking a look at the MSI Z490 Godlike, which is going to be the first of the Z490 PCB breakdowns, just because, well, I actually had a really hard time deciding which board to do first. Like, I spent a lot of time thinking about it, and then I was like, well, ultimately, I'm not going to recommend, like, I didn't want to start with a motherboard that I feel like would be an actual board that I would recommend to people to buy. So this is a motherboard where I think it's a really cool motherboard, but it's also going to be over $700. So I'm not going to recommend that you buy it, even as cool as I think it is. Because the thing, and I think this goes for a lot of the Z490 motherboards in general, is just like some of these boards to me, as somebody who pays way too much attention to things like power delivery and memory overclocking, like a lot of the Z490 boards, it's just like they're just doing things that we've never seen on motherboards before. And I think it's really cool that, you know, we get to I think that's just really cool that these motherboards have that. Like Z490 as an overclocking platform just looks absolutely ridiculous. And anyway, so the first thing I would, and one of the reasons why I ultimately went for the Godlike is look at this. Do you see? Okay, well, you can't actually tell, but this memory setup right here. First, you'll notice that there's no ground shield over it, so which is kind of unique to MSI. Like a lot of the other board vendors are putting ground shields on their boards. MSI isn't. I'm not sure how that overall works out, but MSI is doing something very different, and I'm not sure that anybody else is doing this. And that's this this sort of pattern that we see here with the memory traces. So these are tabbed traces, which is I think, Intel thing. Like, Intel did all the research for it. I'm not sure if it's an actual Intel patent. I read a paper about it, which I think was patent pending. The paper also went completely over my head as far as why this works. But the idea behind these is if you have traces that need to carry very high frequency signals, like say 5 gigahertz DDR4 data for well, your memory. If you do this sort of tab trace layout, essentially what this is doing is instead of just having a memory trace that just kind of goes to the memory controller, and it'll be like length matched and made sure that, it doesn't pick up interference. And there's already like some basic design rules for setting up a DDR4 memory interface. But the thing that makes these special is that essentially instead of just having a regular sort of trace, there's little tabs coming off of it. And if you and then, so if you do this on one trace, it doesn't really do anything. But if you have multiple lines and they're sort of like woven together like that, which I'm drawing it really badly, then you actually get a reduction in, I think, reflections from the ends of the traces. If I remember the paper correctly, I will be linking the paper down in the description because, again, it's just like that. The whole thing is this is the very deep end of sort of electronics engineering, so way over my head. Yeah, so these are really cool because essentially this is, I think, the first time I've ever seen them used on a motherboard. MSI claims that the Godlike is going to be capable of doing DDR4 5000 megahertz, which is insane for a 4-DIMM motherboard. Like for a 2-DIMM motherboard, it's not really that out there, but for a 4-DIMM, like, that is crazy. And yeah, and part of that's going to be the tab traces. Also, this is an 8-layer PCB. The memory topology is an actual daisy chain, so basically you can call this a tabbed daisy chain topology, and I'm pretty sure it is unique to MSI, as in I am not aware of any other board vendor doing the tabbed memory traces. There are other board vendors doing things like ground shields over their memory, but yeah, these I don't know. So maybe this will give MSI a major edge in terms of memory overclocking compared to everybody else, or it doesn't actually do much, and that's why we've never seen it before. Like, I don't know, but I just think it's really cool that we're seeing, a unique new sort of trace layout topology on Z490 motherboards, because yeah, I just like sort of cool, sort of weird design decisions with motherboards like that. Except like there's also weird design decisions that don't make that I don't like. But this is one of the ones where it's like, oh, this is new. This might actually lead to better memory overclocking. I like it. So yeah, and I really hope to get a chance to actually test this board. I have pictures from MSI. I don't yet have a board from MSI, but I really hope I get my hands on one of these. So A, I can test out, if this really gives MSI like a memory overclocking edge. Also because I want to test out the transient response of this VRM, because it looks like it'll be good. So yeah, tab daisy chain, which basically that means these two memory slots are going to be the best for going really, really fast. MSI also says that this motherboard is actually capable of running 4 DIMM slots populated up to 4400. Also, if you have 2 ranks, so if you have 2, so basically if you want to do 5000, 1R, 1R, you want 1 rank in the 2 far DIMM slots, because those are the ones without terminate. Basically the issue is if you put your 1 rank DIMM here, you have a termination problem where you just have a bit of loose wire hanging off the end of the trace, and that causes a bunch of issues. So yeah, but if you're going for 5000, 1R, 1R, then if you're going for 4400, so with a higher memory capacity, you can either go 2 ranks or like 2 ranks and 2 ranks, or you can do 1R, 1R, and so 1 rank in each DIMM. And then if you go for 2 ranks on each DIMM slot, 1 rank in each DIMM slot, and then if you go for 2 ranks in each DIMM slot, MSI says it should be able to do up to 4000 megahertz. I would assume with 2 ranks per DIMM slot, you're going to also be very dependent on how strong your memory controller is, because generally once you hit even at 2 ranks per channel, you end up with the memory controller starting to complain. But if you have like 4 ranks, because like this is 4 ranks on each memory channel, like this is just gonna absolutely murder a lot of CPUs in terms of getting it stable at high speeds. But yeah, so that's kind of the thing, is like also the memory speed gains from motherboard vendors always take them with a grain of salt. Though in recent history, MSI has been actually, like, their claims for like 4800 on Z390 were actually pretty accurate. So yeah, I feel like MSI's claims are less out there than some of the other board vendors that I've dealt with, where it's like the board will be advertised as going up to like 4400, and it's like, yeah, except you need this very, very specific memory kit, and otherwise it doesn't do it. So yeah, anyway, so that's one of the reasons why I'm very excited for the Godlike. Is just the memory topology is like, this is new, cool, new and unique, and I think is really cool. Plus 8-layer PCB, so yeah, this should be like, this is basically as advanced a daisy chain as you can probably get right now. Anyway, other cool things about this board. Down here, we've got an OC fail set button, so that should allow you to, so basically that's going to be like MSI's version of safe boot. So if you screw up if you're bad at saving BIOS profiles and you screw up settings and the system doesn't want to post, in theory you should be able to hit that button and it'll get you back into the BIOS with the last known good settings, or at least that's my understanding of the explanation I got. Which the issue with, so basically it's very similar to the safe boot button that like EVGA has on their motherboards with a safe boot button. The issue with this style of safe boot implementation is that sometimes you can get, the last known good will sometimes remember settings that are actually kind of sketch. So you can end up getting into the BIOS at like memory overclocks where it's like, yeah, scrolling through the BIOS causes it to crash, so I would prefer something that takes you all the way back down to stock settings without, like, boots you at stock settings without wiping the BIOS. But as far as I know, Asus is the only ones doing that. Actually, I think ASRock also has it. Though ASRock's implementation of it is really, like, 1, it's really rare. 2, it's really annoying because the way you get at safe boot working on ASRock boards is you have to mash the button as the board is powering on instead of just hitting the button and the board does the safe boot. No, you have to mash it as it's turning on, which is just... like, it's a little thing, but it's annoying, okay? Anyway, next to that, we have also the OC retry button. So this is like a very hard version of reset. So the reset button there's some safety checks with it. So, for example, if the CPU locks up really hard, the reset button can stop working. So you crash the CPU super hard, reset stops working. OC retry, on the other hand, doesn't care. It basically tells the power supply to cut the power, and the power supply cuts the power, and then it reboots, and then, restores the power and turns on the system again. So this is great. One, if you've really hard locked the system. Two, it's great if you're training like aggressive memory settings for competitive overclocking. You can end up with memory profiles where it's like you need to you need to force the CPU to try boot those settings multiple times before they actually start working. And the retry button is the easiest way of doing that, because on motherboards without the retry button, essentially what you have to do to force retrain the memory controller is you have to cut the power supplies. Like, you have to basically disconnect the power supply from AC power, and then discharge the system, power the power supply back on, and then power it on again. And the retry button just saves a bunch of time by doing all of that for you, essentially. So it's really convenient for training hard memory settings. Other than that, we've got some pretty normal buttons like power and reset. We've got an LED on-off switch, so you can disable the LED, I think all of the RGB on the motherboard. We've got this poorly implemented 6-pin power connector over here. So the idea behind this 6-pin power connector is that it provides extra power to the PCIe slots, because the 24-pin is not really designed for powering like 3 or 4-way GPU setups. There's just one issue with the way MSI has implemented this. It sticks straight up. So if you plug in if you plug in 3 GPUs into the motherboard, guess what you're not going to plug in? You're not going to be able to plug in that 6-pin, which is why I don't think it should have been, like, they should have just not bothered with it. Admittedly, on past Godlikes, they would put it like sort of in the middle of the board, and I'd complain that that's a stupid location, because now you have a power cable running across the center of your motherboard. There's just really no good way to route that out, route that power cable. But yeah, no, this is worse. This is just straight up worse. I guess if you're running LN2 GPUs, you might get away with it, because they're, well, yeah, you might get away with it as long as you don't have like a tall VRM heatsink or something in this area, because the GPU cooling will, or if you have a universal GPU block, then you might get away with it, because generally, you'll have something tall in this area, and then this area of the PCB will just be VRM. So you might be able to plug in the 6-pin that way, but if you have regular air-cooled cards, there's no way you're plugging that one in. So it's kind of dumb that it's even there. I don't get why we don't have that. Like, why hasn't anybody ever put that 6-pin power connector, like, here or something? Right? Like, the 24-pin, I think the 12-volt... Actually, I can't remember where the 12 volts is, but I think 12 volts is, like, it's on the edge of the connector. So you just kind of go like that, and then, like... And it's not in a stupid location, and it's easily accessible. It doesn't get in the way of anything. But no, nobody ever puts it there. Everybody puts it over here, or they put it along the bottom edge, and then they don't angle it, and you can't plug it in. Gigabyte also did this. Like, Gigabyte's X570 Aorus Extreme has a 6-pin power connector on the bottom edge of the motherboard, which you cannot plug in if you run 3 GPUs. And theirs is actually worse, because theirs is right here. So, like, there is no way you're ever plugging that one in. But yeah, like, if you're going to put a 6-pin on the bottom edge of the board, it should be at a right angle. So, because otherwise you completely just defeat the purpose of having that connector. The board also has a dual BIOS switch, which I'm a big fan of, because if you're testing whether a new BIOS update is better than a previous BIOS version, you can flash the new BIOS onto one of your 2 BIOS chips that's built into the board, and then you can very rapidly go back and forth between the 2 BIOSes to, check any sort of overclocking disparities between them. So yeah, I'm a big fan of having dual BIOS on a motherboard. Then over here we have some fun LN2 jumpers. So this is JLN1 and JLN2. They essentially exist to make you look make you look like a competent overclocker if you don't know what you're doing, because JLN1 is meant to remove cold bugs, and JLN2 is meant to remove cold boot bugs. Normally, the way you deal with those 2 issues is you have to dial in a bunch of voltages in the BIOS to get the CPU to boot at really low temperatures. Well, with JLN1 and JLN2, you don't actually need to know what you're doing with your voltages. You just you just use the jumpers, and the motherboard does it for you, and you look far more competent until you run into one of the rare CPUs that isn't actually compatible with the presets that the motherboard comes with, and then, you have to do it the hard way anyway. But yeah, this is a cool feature for saving time if you're, just getting into extreme overclocking. Unfortunately, it's also on a $700 board, so, well, the board is $700. It's over $700, and you might be like, you might be wondering, why is the board so expensive? Well, part of it is all of the Z490 motherboards are designed to PCIe 4.0 standards, or actually not all of them. I don't know that all of them, but a lot of them are designed to PCIe 4.0 standards, which basically means more expensive PCB substrates, more expensive PCIe switches and repeaters, and just like you have like basic components that have to be physically present on the board just now are now more expensive because they're designed for PCIe 4.0 instead of 3.0. So that's part of it. But also with the Godlike series, like these boards are just ridiculously expensive because MSI just does whatever the hell they want in terms of feature set. And I'm a big fan of that, right? That's why we have JLN1, JLN2, retry, safe, OC fail set over here, the dual BIOS. Like the board kind of tries to do everything. I just wish we could go back to, like, I miss having the full on like extreme overclocking targeted boards where you'd have like BCLK controls built on the BCLK up down buttons, ratio up down buttons. I'm surprised we never got voltage controls on a like board, like a hardware level. I think that would be really cool because you could maybe because if you're messing with like sketchy memory settings, you could try booting at different voltages without ever going to the BIOS or something like that. But yeah, like the thing is, currently MSI, like the Godlike boards get a bunch of extreme overclocking features, but at the end of the day, they're still sort of meant to be gaming boards. So like targeted gamers with way more sense, with way more money than like sense. So unfortunately, you can't get the full extreme overclocking loadout that you used to get on older generations of boards. But hey, this is a lot. Like dual BIOS is more than you get on a lot of motherboards these days. Anyway, other features for overclocking. We've got BIOS flashback, so you can update the BIOS of the motherboard without even having a CPU installed. In theory, that should also be able to recover corrupted BIOS flashes. So if you have like a power outage while flashing the BIOS, you might be able to recover that with the BIOS flashback button. So that's really cool. There's also a clear CMOS button. So, if you're a normie and your motherboard's in a case, and then you punch in a bunch of memory settings that don't work, or just set the CPU core voltage to so low that the system is no longer able to boot, you can hit the clear CMOS button and you're back to stock settings, and you don't even have to open up the side panel to find the jumper on the motherboard, right? Like, far more convenient. So that's nice. Overall, the rear I/O for the Godlike, well, here it is. Looks a lot better than, say, the X570 Godlike. Also, what I find absolutely hilarious is, like, there's a new trend, like, the new thing in the motherboard industry is to integrate the rear I/O shield to the motherboard, right, so that people don't forget to install it. But the thing is, MSI, for some ungodly reason, decided to put fans for VRM cooling in the in the I/O shroud. And here's the thing. The VRM on this board barely needs heat sinks. So the only reason to bother with putting fans into the VRM, into the I/O round is basically I'm assuming MSI is aiming to hit like 50-degree operating temperatures on the VRM or something stupid like that. And it's just like, it's a VRM. As long as it's well below like 90 degrees, it's at perfectly acceptable operating temperatures. Like, actually, even 90 degrees, I would consider a perfectly acceptable VRM operating temperature. Like, it becomes a problem if it's over 100, okay? This right here, like, I'll be surprised if this VRM goes over 100 degrees with no heat sinks, okay? So, having frickin' fans for the heat sinks on the VRM is just like we've basically, it feels like we've gone from one extreme to the other extreme. It used to be that a lot of motherboards would have terrible VRM thermals, and now we have high-end motherboards that really don't need any more VRM cooling than they already came with, getting freaking fans because I guess they want to I guess the board vendors now just want to get the top spot in like VRM comparison charts, and it's just like, but it's a waste of space on the board, and it, like, no fans. Just no fans. This is a Z490 motherboard, no fans. If this was like a TRX 40 motherboard, I could understand the decision to include some fans for VRM cooling. If this was a X299 motherboard, I could maybe kind of understand including some fans for VRM cooling. But this is a mainstream Intel board. The 10900K is going to pull a lot of power, but it's not going to pull that much power. You don't need fans. And the funny thing about the fans, though, is now you need to put holes in that integrated rear I/O shield. Like, which the best part is like if you didn't have the rear I/O shield at all, if it was just not there, those fans would get much better airflow. But yeah, so first of all, the fans are dumb. Secondly, the rear I/O shield restricts airflow to said fans. So that's dumb. And so then they put holes in the like we have like multiple levels of self-defeating design decisions here. It's like, one, the VRM doesn't need fans. Two, the rear I/O shield is blocking airflow to the fans. So now it's like, yeah, I'm not really a fan of this. You get 10 gig of Quantia. That's that over there. You get Thunderbolt. There's this 2.5 gig. That's Realtek. And what else do we have? Oh, that's kind of it. Oh, you get Wi-Fi 6, right? And unlike the, say, the X570 Godlike, this actually has a rear I/O section worthy of an eATX motherboard, right? This thing is not ATX. It's quite a bit wider. Oh, I forgot to mention there's voltage read points. There's also a postcode over there. This LCD, like, I'm actually not sure if it's, like, you have the screen thing on the board that I kind of forget that the Godlikes have. Like, it always surprises me that it's there. Because it's just not something I think about. It's like, I want a postcode. I don't care about the big screen thing. You've also got some basic troubleshooting LEDs over here that are all the same color, mashed right next to each other in a really hard to see spot on the motherboard, but luckily they're made completely redundant by the postcode, so that doesn't really matter. Yeah, so rear I/O section looks fine, and at this point, let's talk about the VRM. So this is a VRM that MSI is actually using on, I think, several boards. So if you want the if you want this monstrosity of a V-Core VRM, you don't necessarily need to buy the Godlike, which is kind of neat. Also kind of defeat, basically if you're buying a Godlike, you're not going to be buying it for the VRM. You're going to be buying it for, you know, the OC features down here. The very unique, like, the thing is, the tab daisy chain, MSI is doing that on all of their motherboards. The tab traces, they're doing that everywhere, even their ITX board. The thing is this is an 8-layer version of that. So compared to the 6-layer ATX boards, this is going to have an advantage in terms of memory overclocking, just because they can, you know, put more layers into the memory layout. So this is like, if you want an ATX motherboard from MSI with great memory overclocking support, that's kind of like the best memory overclocking support. That's the Godlike. As their ATX boards are still going to be really strong in the memory overclocking department, which is just in general with Z490 there's a lot of strong memory overclocking boards. But yeah, if you want the strongest MSI has to offer and you don't want an ITX board, this is the only option, because like the VRM, on the other hand, is something you can actually get, I think, all the way down to the Z490 Unify. Like, this VRM is not unique to the Godlike in MSI's lineup, and actually Gigabyte has a very similar version of this VRM on the very similar version of this VRM on the Z490 Aorus Extreme. So, yeah, this is not, like, the VRM here is, to me, not the highlight. Anyway, this is a monstrosity, though. So V-Core is a 16-phase. Then over here, we've got 1 phase for the iGPU, which is a very welcome addition, because the Z390 Godlike didn't have an iGPU VRM at all, which basically meant if you wanted to use the QuickSync video encoder built into, you know, Intel CPUs, you couldn't, because the iGPU is the thing that the encoder is dependent on the iGPU being functional, and if your motherboard doesn't have an iGPU powered, doesn't have a VRM for the iGPU, well, guess what? You can't turn, the iGPU doesn't run. So, yeah, now we have an iGPU VRM, which that's good. And then down here we have a VCCSA VRM. And the reason why I've highlighted all of these different outputs right now, is that the way this VRM is controlled, the controller for this VRM is that chip over there. And this is a very big chip, you may notice, because that chip has a lot of phases. That is an ISL 69269. it goes up to 12 phases total, and it does 3 outputs at the same time. So here it's running as an 8 plus 1 plus 1. There are some motherboards out there running it as a 12 plus 0. There are also some motherboards, like I think there's a motherboard running it as an 11 plus 1, which is a really, that's a funky VRM configuration, having an 11 phase. Like, this is pretty unique. But anyway, so here it's running as an 8 plus 1. So the 8 obviously goes into a bunch of doublers, which we can find on the back of the board, which is all of these chips. And then the plus 1, that's for the system agent and the iGPU VRM, right? But anyway, so that's all of our doublers. These are ISL 6617s. These are basically as smart a doubler as you're going to get. So they can current balance, they can interleave, they can synchronous and current balance. So in synchronous mode, the idea is basically if you have interleaving, you go from 8 phases to 16 phases as every single phase turns on independently, well, somewhat independently of every other phase. Synchronous mode bypasses the interleaving, and essentially you can turn on two power stages at the same time, which puts them in phase with each other. So if you have synchronous mode running all the time, this would be an 8 phase. Now, as like a lot of motherboards use ISL 6617s permanently locked in synchronous mode because it gives you a transient response advantage. But I think they still current balance even through synchronous mode, so you still get a efficiency advantage over just kind of like mashing a bunch of MOSFETs into one phase. Instead of like not going with an ISL 6617 at all. The other thing is, I'm not sure that the ISL controllers can actually deal with having 2 power stages on like one current input without going through a doubler like this first. Because the thing is, like, this thing does a bunch of, like, this thing actually sums up the currents of the 2 phases and then passes that back to the controller. So the controller doesn't have to deal with the complexity of there being, 2 phases on one PWM line, whereas there are other controllers that actually kind of work around that. But anyway, this control scheme is, it can be a 16 phase, it can run as an 8 phase. Ultimately, I think MSI is actually running it as the 16 phase option. 1, because they don't really have much in the way of input filtering. 2, because the inductors that they're using are relatively low inductance. Yeah, I'm not 100% certain on that. Either way, I don't also really care that much. The main thing is that's the control scheme here. So this can go up to 16 phases. It's not necessarily, it doesn't have to be 16 phases because those doublers can also not double. The thing is, ultimately, like, I also, like, the thing is with the doublers is the main argument against using doublers in VRMs these days, at least if you're Asus, is that they make your transient response bad. My counter argument to Asus is that the best motherboard for transient response on Z390 is the EVGA Z390 Dark, and that uses a bunch of ISL 6617 doublers. So evidently, they don't make that much of a difference. And with what does, however, make a big difference to transient response is your capacitor configuration. And I like, that is the output filtering for the vCore. And you'll notice that these are SMD aluminum polymer capacitors. And I'm a big fan of these because these have extremely low ESRs, extremely low ESLs. They're also very expensive, which is why you only see them on the Godlike. And like, there's more, well, actually with Z490, there's quite a few boards that now take advantage of sort of these high, like very expensive SMD capacitors. But yeah, MSI only uses them on the Godlike because these are potentially like 10 times the cost of your, conventional through-hole capacitors. So, and they're only really necessary if you're absolutely, like, hell-bent on having the best possible transient response. So that's one of the main reasons I'd really like to get a chance to test this board in terms of transient, like, voltage regulation, is just, like, one, the capacitor actually, it's entirely because of the capacitor configuration. It's just, like, this should be absolutely amazing for transient response, because that is a lot of that's a lot of SMD capacitors, and they just work really, really well. That's like the Z390 Dark is a perfect example of that. That admittedly used tantalum SMD capacitors, but still, like, that thing was the best board for transient response. It wasn't like massively better than some of the other boards, but it was still the best. Like least overshoot, least undershoot. And there was like a board I tested that matched on the, actually there was a couple boards that almost matched it or matched it on the undershoot, but there was not really any boards that beat it, like also had the same level of overshoot, like same low overshoot as the dark did. So, but I never got a chance to test a Z390 Godlike, which is why I'd like to test the Z490 Godlike, because yeah, I'm a big fan of SMD capacitors. Anyway, so that's kind of the sort of control scheme, transient response considerations for this VRM. Let's talk about the actual power stages, right? The thing that makes sure that, because there's two factors to a VRM, right? There's part one, where it's like the VRM has to not overheat, okay? If the VRM overheats and burns up and dies, it has failed as its job of being a power supply. The second thing it kind of needs to do is it has to deliver well-regulated voltage to the CPU, and that's where, you know, the capacitors and the controller and the doublers and the inductors come in, and that's basically like, do you have a good transient response? Do you have low ripple? That's where all of that comes in. But the power stages are primarily about making sure that the VRM doesn't overheat. Though there are some considerations where it's like the power stage can affect transient response depending on like how fast the MOSFETs in it are, but power stages are just way faster than discrete MOSFETs, so that's not really a consideration. Anyway, so the power stages MSI is using here are ISL 99390s. These are 90 amp smart power stages, which means they integrate a very accurate current monitoring. They integrate temperature monitoring, a bunch of safety features like short circuit protection, over current protection, over temperature protection. Basically, these are meant for servers. That's kind of the idea. And also, you won't find a server motherboard with this many of them. Which is kind of the funny thing about like high-end gaming motherboards is they generally have better power delivery than anything that would ever end up in a server. And just because servers actually care about having like relatively efficient CPUs, whereas if you're really like pushing the limit with overclocking, your CPU efficiency just absolutely falls off a cliff, and the amount of current that a CPU can end up pulling is absolutely stupid. So let's talk about how much heat this VRM produces. For a variety of different current outputs. And the funny thing is, this VRM, like with 16 phases of 90 amp smart power stages, makes it kind of pointless to discuss any amount of current output less than like 200 amps, because if you're below 200 amps, most of the VRM should actually turn, like a good chunk of the VRM should turn off. Which the controller can do. This is the 69269. Like, depending on how the firmware is configured, this VRM will run on fewer than the maximum number of phases to maximize efficiency. MSI also has a setting in their BIOS to just force enable all the phases all the time, which can potentially lead to slight improvements in transient response in certain scenarios. Not always, though. Anyway, so 1.2 volts output, 500 kilohertz switching frequency, which is just the switching frequency that these power stages are spec'd at. You're going to see the following efficiencies. 200 amps output, this VRM is going to produce about 15 watts of heat. That means, at 240 watts going into the CPU, which is very doable, okay? Running 240 watts into a 14 nanometer 10-core Intel CPU is very easy. You're probably going to need a bit more voltage than 1.2 volts to do it, but you can definitely do 240 watts of power consumption. And with the optimizations Intel has done to the the thermal design of the 10900K and the 107, I think all of the K SKUs have the optimized thermal design. With the optimizations that Intel has made to the cooling of the CPUs, now it's even easier to shove ridiculous amounts of power into your CPU. So that just, makes more work for the VRM, though this VRM really probably, doesn't care. 200 amps, no big deal, 15 watts. 300 amps is going to produce 23 watts of heat, which is, good luck cooling that. Is what I want to say mostly, is good luck cooling that, because at that point you're going to be looking at 360 watts of CPU power consumption, which is actually coolable. I'm just not sure how coolable that is on a manufacturing process as dense as 14 nanometer, because like you could do 360 watts on like X79 quite easily. And 300 watts on X99 was also very doable. And X299, you know, if you have like the 14, like 12 core, 14 core, 16, 18 core, those chips can do 360 watts up to 450 watts, even 500 watts quite easily, and it's coolable. It's just that those things are like those are huge chips, whereas these are kind of small. So it'll be interesting to see, you know, but like the board might actually be required to pull three. Like I can definitely see cooling systems that would be capable of dealing with a 350 watt, 300, or even 400 watt 10900K. Like that should be doable. Which is why this VRM is like. I mean, it's still super overkill because that's 23 watts spread across all of these power stages on a 8-layer PCB. Like this VRM really shouldn't need a heatsink ever, as far as I'm concerned. Well, except maybe if you were running Prime 95 on like liquid nitrogen, it might need the heat sinks. But otherwise, yeah, no. So the VRM here is just awesome and epic and just amazing. And there are other boards with this VRM, so you don't have to go for this one. It's just, yeah, this one has the advantage of also having all of the lovely SMD capacitors. Doing 400 amps output, this VRM will produce about 34 watts of heat. So now we start getting into a heat output where it's like, having good heat sinks starts being actually important. Going up to 500 amps, produces 48 watts of heat. So that's about 600 watts of power. At this voltage, that would be about 600 watts of power going into the CPU. So, yeah, this VRM is absolutely ridiculous. And then 600 amps, it'll produce about 66 watts of heat. I didn't really like... We could go on, because these are technically 90 amp smart power stages, and this is a 16-phase VRM. It is worth noting that the data sheet for these actually stops at 60 amps. It doesn't go all the way out to 90 amps, because practically speaking, the 90 amp rating on any, or even the 60 amp rating on a power stage is normally in a very unrealistic cooling scenario, as in the power stage would not be next to a bunch of other power stages in a big VRM. It would be just kind of sitting on its own on a very large evaluation board where there's not really any other heat producing components anywhere near it, which is why it can reach such a high current output in that kind of test scenario. So yeah, I could go and calculate the heat outputs up to some stupid number, but honestly, even I don't think you can do 600 amps even on LN2. Because the thing is if you run liquid nitrogen on really anything, the actual current draw for a given voltage, the current draw goes down. So the overall power consumption actually ends up really high, but that's because you're going to be running a high voltage, not because there's going to be ridiculous amounts of current flowing into the chip. So you might end up with something where you're doing 600 watts, but it's 600 watts because you're running 400 amps at 1.5 volts rather than, pulling 500 amps at 1.2 volts, which 400 amps at 1.5 volts is actually less difficult for a VRM to do than 500 amps at 1.2 volts. So, yeah, there's just no point going past that 600 amp figure as far as I'm concerned. And even on LN2, I doubt you'd be able to reach it. So yeah, this VRM, continuing the trend of previous, godlike motherboards, is just ridiculous, insane overkill. And it's this time around, it's even more ridiculous, insane overkill than some of the past entries in the motherboard. No, it is. I need to pull up notes for some of the past godlikes, but. Yeah, this is the first one with 90 amp smart power stages, though the thing is 90 amp smart power stages only started being available this year, so I'm sure if they existed earlier, MSI would have used them, but they didn't. So yeah, anyway, so that's the V-Core. The iGPU VRM is another ISL 99390, so your iGPU is definitely not going to be starved for power while doing its little video encoding, which I assume is the main use people would have for the iGPU on a board like this. VCCSA, we have two discrete MOSFETs. These are just on semiconductor NC, 4C029 for the high side, and a 4C024 For the low side, both of the, like, VCCSA is not a particularly high current rail, so this is more than enough. Like, this is actually like one phase in a low-end motherboard VRM. So for something like VCCSA, which is basically just like the interconnect in the in Intel CPUs between like the memory controller and the PCIe and the cores, you don't need a massive VRM for that. Then down here we have a bunch of minor voltage regulators for the VCCIO rails and the various because there's a bunch of minor voltages for extreme overclocking. And I'm not going to highlight all of them, but yeah, the voltage regulators for that are in sort of this area. And these would be the two VCCIO rails because those are the high power ones. And then these I assume are going to be like VCC PLLOC and VCC VTT or some other minor voltages like that. So that's all in that area. We have a dedicated clock gen on the motherboard. So for those of you, oh, they do actually have the motherboard name on it. Man, I did not notice that. It normally is in big white letters, right? But yeah, they do have it. It's just in black, so you can't see it. But yeah, there's a dedicated clock gen on the motherboard, which is a standard feature for high-end Z490 motherboards. It's been on even Z390 motherboards. Like the thing is with Skylake, Intel actually went out of their way to separate the BCLK from the PCIe and SATA interfaces. So if you have a K-series CPU, you can run very high BCLKs, and the reason why you would want to do this is potentially for memory overclocking. Though with I think Z370, Intel introduced an absolutely ridiculous number of memory ratios. So the BCLK, like it used to be that if you were on, say, Z270, the only way to go above like 4133 megahertz was to raise the BCLK. So if you wanted to run like 4800 megahertz on a Z270 motherboard, you had to run like 130 plus BCLK, I want to say. But on actually no, not that high. You'd need like if you went from 4000, you'd need like 120 megahertz BCLK from 4000 megahertz to go 4800. So yeah, Intel basically gave us the option for K SKUs to run arbitrary BCLKs. Non-K CPUs unfortunately have that functionality disabled. So yeah. But that's why having dedicated clock gens on motherboards is useful, is if you wanted to also like run a overclock where you're running like 5.15 gigahertz instead of just straight 5, or instead of like 5.1 gigahertz, you can run 5.15 by running 101 BCLK and 5.1 gigahertz, and that's actually like perfectly valid, and it's not going to cause any issues because the BCLK doesn't affect anything other than the memory and the CPU core ratio and the uncore ratio, right? Which makes sense. So basically, the BCLK now only affects the CPU things instead of everything, which is cool. And that's why we get clock gens on Z490 boards. And you also get them on X570 and stuff, but there have been platforms where it's like having a clock gen on a motherboard just doesn't do anything because the CPU, like your PCIe will drop out at 107 BCLK. So, it's just like, why would you do that? Anyway, we've got two-phase memory power hiding under the screen. The thing with the memory is just like DDR4 does not pull that much power, so it doesn't really matter how you power it. A lot of the high-end boards will actually just have single-phase memory VRMs, and it works just fine. And actually, a lot of the like crazy high memory clocking ITX boards will have single-phase memory VRMs because you physically can't fit a two-phase on an ITX board a lot of the time. So, yeah, but two-phase memory power, which is also just a sort of default feature of Godlike motherboards from MSI, where it's they have two-phase memory power just because they can, not really because it does anything. Like the memory VRM is far less important than something like the actual topology of the memory itself. So yeah, anything else worth talking about? BIOS flashback, we measure clear, and I love how my notes say stupid 6-pin. Like, that's what my note about the 6-pin is just stupid 6-pin. Yeah. Okay, admittedly, I wrote the notes, but past Buildzoid made good decisions with my notes. Yeah, I'm not seeing anything worth that I've forgotten at this point. Oh, wait, there's a slow-mo jumper. Yeah, there's a slow-mo jumper over here, which is basically for LN2 overclockers to force the CPU into the slowest frequencies. And this can be convenient for like saving screenshots and idling without pulling too much power. That's like the main use I've had for slow mode is just like you can temporarily drop the CPU to like 800 megahertz, take your screenshot, and then go right back to full speed and run whatever benchmarks you want again. So yeah, that is the Z490 Godlike. You've got, all of the things. Unfortunately, at also the biggest of price points, right? So this is a motherboard that I think does a lot of really cool stuff, and that's kind of why I decided to do this motherboard first, because we've got, like, especially the tab daisy chain, like the tab traces, really cool. And then we've just got the standard insane VRM, the well, the insanity level of the VRM has gone up, but past Godlike still had insane VRMs, so that's not really new. And then we have a lot of the, like, I actually feel like we have more extreme overclocking features than there have been in the past. Like, I'm not, well, like, retry is, I think, like, new. I think. And the fail set, like, well, depends if you compare to, like, X powers, but yeah. So this is a board that I wouldn't recommend you buy, but I think it is a very really cool board. If you like ridiculous motherboards. So yeah, that's it for the video. So thank you to MSI for providing the pictures. I really hope I get to get a chance to actually like test one of these in person instead of just getting to look at pictures and go like, oh my god, this looks so cool. Yeah, so thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. And then there's also the AHOC Teespring store where you can buy, the usual YouTuber merch like shirts, stickers, posters, that kind of thing. And that also helps out immensely with running the channel. So there's a link to that down in the description below as well. And that is it for the video. So I'll go hit the stop button.